Hey everyone. So today what we're going to do is to go over decision trees again, and then afterwards I'm going to give you a crash course in probability, and then afterwards we're going to use Radiant to analyze a dataset given to Rady by Citybikes, which is a company in New York. So first, go to the Dropbox and click on TA Sessions, TA Session 1, and open up the TA Session 1 decision tree practice. Okay. And I kind of gave you like the main case study for the San Carlos mudslide case. What I want you to do is to spend maybe 5-10 minutes reading this and solving this problem. So the first thing to do, even before inputting anything in Radiant, is to just sketch out the tree, because it's kind of complicated to, especially in harder problems, you put everything in Radiant and then you're not sure whether or not you did it right. So it's just a good idea to have, to know what the tree should look like before you even plot it in Radiant. So that's what we're going to do. Okay, so the first thing is that you're deciding whether or not to build a wall to protect against the mudslide. So your decision, you have an initial decision of, and we're gonna color decision nodes green squares like in the Radiant plot. So to build the wall or to not. And then if we don't build the wall, then what happens? Okay, if she decides not to build the wall, then if the mudslide hits her shot, okay, so then there's an event node here, which is that there's a chance that the mudslide hits, so the mudslide hits, or it doesn't. Right? And then, okay, so if that's it, then if you don't build the wall, then either the mudslide hits or it doesn't, and then you just get your payoffs here. Right? But if you do build the wall, then there's another event node. If you build the wall, then okay, so then there's a chance that this wall could break. Okay, so if you build the wall, then there's a chance that this wall could break. Color it orange. Okay, so there's this event here that this wall could. Oh, but then let me think. First thing to ask yourself is, which event comes first? Does the wall break, or does the mudslide hit? You have to think about that. Okay, so in this problem, it's pretty clear that it should be the case that the mudslide hits first before the wall can break, right? Because the wall's not going to break randomly, or the wall's not going to break before the mudslide hits. So it's the mudslide that comes first before the wall breaks. Right? So here it's break and not break. Right? So in this case, it's kind of clear that the wall would break only after the mudslide hits. In other problems, you have to think about it a little bit more, which event comes first. And a good question to ask is, at this point in time, at this node, do I know whether or not the mudslide has occurred? If the answer is yes, then that means that the mudslide or that event happened before this chance node or this decision node here. Right? So when the mudslide, or when the wall broke here, we already know that the mudslide hit, so that's why the mudslide should come before the wall breaking. Okay, it's pretty clear here. In other examples, it might be a little bit harder. But anyways, so this is what the tree would look like. Right, so, okay, so now we have what we're looking for. The next thing to do is just put it in Radiant. Okay, we're in Radiant, so you go to the decision analysis tool. And in your homework and on the midterm, it's open book, so you can use any of the decision trees that we've gone over in class to sort of build your new decision tree, right? So you don't have to, learn the syntax and well, you do have to learn the syntax, but you don't have to start from scratch. You can build off of this this decision tree, or maybe the ones that are already in the Dropbox. In this case, the tree is already in the Dropbox, but we want to build it kind of from scratch. So let's look at what this tree looks like. This tree for the signing the contract looks like this. Our tree, the one that we want, looks kind of like this. So it's not it's well kind of the same. You have two decision paths in the first decision node, but then afterwards it kind of looks different. Right? So then, okay, so I'm going to modify this a little bit. This first decision node is to build wall, and the other one is to maybe not build wall. Okay, and if you don't build the wall, what happens? Two things can happen if you don't build a wall. So you just copy paste that over. Make sure you you tab it correctly, right? So two things can happen: either mudslide hits, or it doesn't, right? Not mudslide. No mudslide. And according to the probabilities, what's the chance of the mudslide hitting? There's a 1% chance of the mudslide hitting her shop in the next 10 years. Okay, so the probability would be 1%, and this therefore is 99%. And if it hits, she'll lose $1 million. Okay, if it hits, she'll lose $1 million. Okay, and if it doesn't hit, then she doesn't lose anything, right? Because she didn't have to pay anything, she didn't lose anything. Okay, but if she decides to build the wall, then there's this event. There's actually kind of the same thing as before. Oh, and by the way, there's a cost here. Say wall cost, right? And the cost of the wall is $40,000. So we can just put that, and we're gonna call it the wall cost. Right. So let's see how. Okay, so if we build a wall, what's going to happen? There's a chance that the mudslide doesn't hit, and that happens with 99% probability, and it doesn't hit, we don't get hurt. But then if it does hit, and since we built the wall, it's not like we're going to get hit. There's going to be another chance node, right? So let's just copy paste that over. It's going to be kind of a chance node within a chance node, and just make sure that we have the right indentation. Right. Then let's see. The wall will break with, okay, so the wall will stand with 95% probability. So let's say this is not break, and this is break. This breaks with 5% probability and stands with 95% probability. If it breaks, then you lose the $1 million that your store was worth. And if it doesn't, oh, sorry, so this should be the other way around. Okay, so if it breaks, you lose that $1 million. If it doesn't, then you don't lose anything. And I think, let's just rename this, I don't know, San Carlos wall. Whatever you want to call it. Whatever you want to call it. Okay. And, oh, okay, so now we have a problem. Let's see. We have some indentation issues. Lines 8. Okay, so this is no problem. We just fix it. We'll just fix these things. They have to have the same. They have to be like that. So you don't have to memorize anything. If there's an error, then Radiant will tell you what the error is, and then you just fix it. Right? And you can see if this tree matches what we have in what we thought. Let's just compare it. See? And yeah, it looks exactly like what we thought. Right? Okay, so now you just do your plot, and it says that you should not build a wall because the expected value of not building the wall is minus 10,000, whereas if you build the wall, it's minus $40,500. Okay, so the answer to the first question is no. Right? Okay, so if so, then how much more could or should the construction company have charged her for this wall? And if not, then what's the most she's willing to pay for this wall? Okay, so suppose that there was no cost. Suppose that the wall was free. The construction company is willing just to charge nothing for this wall, right? Then what is the expected value of building the wall versus not? Well, it's minus 500 here because you're better off building this wall. It's going to be free and it protects you against this mudslide risk. And so you're definitely going to build the wall because it's free. Okay? But now, if the cost becomes too high, then we saw that you end up not building the wall. So somewhere between free and the $40,000 that it was charged at, somewhere between $0 and $40,000, there's going to be this price point, which makes these two numbers become the same, right? If the wall is free, then the expected value of building the wall is minus 500, and it comes from just the risk of the wall breaking. If the wall is not free, if the wall is some price, call it price P, then the total expected value here is minus 500 minus the P that you're paying. So let's just write that down. Okay. So if you build the wall, let me write this here. So if you build the wall and it costs price P, then the total cost is that minus 500 from just from the expected losses in the event that the wall breaks, minus that P that you're paying for the wall. Okay? And on the other hand, if you're not going to build a wall, there's nothing to worry about the cost of the wall or anything. So the expected value is just that risk of the mudslide, which is that minus 10,000. So that's going to be that minus 10,000. And so what price makes these two equal? Right? What price makes this equal? Then you're solving for minus 500 or minus P equals minus 10,000. So therefore P must equal 10,000 minus 500 or $9,500. At this price, these two will be equal to each other. The flower shop owner will be indifferent between buying the wall or building the wall and not building the wall. So this is the most that the construction company can charge in order to make the flower shop owner be indifferent between paying and not paying, or buying and not buying. Okay, let's just see what that means. I'm saying that if this wall cost was $9,500, then now I'm going to predict that the expected monetary value of building is going to be the same as not building. So let's just see if that's true. It's got to be true because that's what we solved for. Right? So it's the 10,000 and 10,000 here. Okay. So that's how you solve this. This question is how much should the construction company have charged you for? That's how you answer these kinds of questions. Okay. Okay. The last thing I want to show you relating to this is sensitivity analysis. And what this is sort of, you have in your model, you have maybe variables that were defined, and you're kind of wondering what happens if the variable values change a little bit or change a lot. And so in this case, we're going to see what happens if the wall cost changes. We know that there's going to be some sort of switching between building and not building when the wall cost is $9,500. If it's lower than that, then you're going to build a wall. If it's above that, then you're not going to build a wall. And we want to see how that what that looks like in terms of a plot. Right, so let's see. See, we have, say the wall cost went from 8,000 to 1,200 in steps of 500. Okay, let's just add this variable that we want to have this sensitivity analysis over. So we add that variable. and then we just evaluate the sensitivity analysis, and it will give us the expected payoff of choosing building the wall versus not building the wall. So you can see here, building the wall, as that wall cost gets higher and higher, the expected value of building the wall gets worse and worse because you have to pay more, right? Whereas the expected monetary value of not building the wall is the same because you don't have to pay anything for the wall, right? And so at $9,500 is when they're equal. At this price point, the flower shop owner will become indifferent between building the wall and not building the wall because they're the same expected monetary value to her. There's no one doesn't dominate the other. Okay. So this is how you do sensitivity analysis, and this is how you think about decision trees in general. What we're going to do is we're going to sort of build up the foundations of probability so that you can build more complicated decision trees where you're updating your beliefs about the likelihood of a mudslide. And we saw that in class the other day where the decision tree got really complicated. And we're going to go over that in more detail so that you understand it better.